Welcome to the presentation of our work, Multi-Object Discovery by Low-Dimensional Object Motion. Optical flow is the apparent 2D motion field observable between two images. In other words, it is the movement of each pixel between two images. For example, here, we can see the optical flow caused by the camera movement between the image at time t and t+1. Let us consider a static scene. Previous work have shown that given an image of a static scene with only camera motion, the optical flow is a linear combination of exactly 6 optical flow vectors, denoted here as f1 to f6. The coefficients of each of these vectors is in fact the components of the linear and angular velocity of the camera. Therefore, these 6 optical flow vectors are in fact a basis for the space of possible optical flows for this static scene. It has been shown that each of these flow vectors can be calculated using the depth map of the scene and the intrinsic camera parameters. In practice, knowing the actual values of the intrinsic camera parameters is not necessary, and we simply assume that the horizontal and vertical focal length are equal to each other and that the principal point of the camera is at the center of the image. We extend this formulation to the case of dynamic scenes. We propose to create a separate basis for each region independently. For each region, we create 6 basis vectors that explain the motion of that region. In other words, for a scene with k independent regions, we create k times 6 basis vectors in total. Our methodology is as follows. During training, given an image, we input the image into 2 separate networks, a segmentation network and a depth estimation network. The depth network estimates per pixel depth map for the input, and the segmentation network segments the input image into a predefined number of regions. Using the estimation of our 2 networks, we create k times 6 vectors that are a basis for the space of all the possible optical flows of this dynamic scene. Then, given the actual optical flow of the scene as input, which can be either ground truth or estimated using an off-the-shelf network, we project that input optical flow into the space spanned by the basis vectors and obtain the projected flow. If the basis vectors are accurate, then the input optical flow should be close to the projected flow. Therefore, we use the L2 distance between the input flow and the projected flow to train our networks without using any ground truth, segmentation masks, or depth map. During inference, we can simply input the image to our trained networks and obtain the estimated segmentation masks and the depth map. We have experimented with both synthetic and real-world datasets. The movie datasets, namely movie A, C, D, and E, are synthetic datasets where the complexity of the scene increases as we go from A to E. We show state-of-the-art results on segmentation on the more complex movie C, D, and E datasets. We also evaluate our performance on the Clever and Clevertext synthetic datasets. Again, we achieve state-of-the-art results on these synthetic datasets. We also use a real-world Davis 2017 dataset to evaluate our method. We show state-of-the-art segmentation results on this dataset as well. We also evaluate the performance of our depth estimation network on the Kitty dataset containing real-world driving scenes and show comparable performance to previous depth estimation methods. Please visit our project webpage for more details and results.